everybody. So today we are going to present an innovative approach using which we can unify and elevate the model selection and comparison process. So presenting to you our research paper on model fine-tuning, a unified platform for model comparison. So we all have been in the field of Gen AI, and we know how volatile this is and how exponentially this has been growing. In last 1 year, we have seen multiple models getting introduced from GPT 4.0, 4.0 Mini, O1, O1 Mini from OpenAI, Gemini from GCP. We have Claude from Anthropic, and the latest and the greatest one, DeepSeek R1, which have been in the headlines from past 1 week. It has almost caused a tech disruption, and with the bold claims that it has and the results it has to offer us, we all have been through the research papers and we have tried it on the dashboard, and it is working pretty well for the STEM use cases and for the reasoning tasks. So now the question arises that with these many models in our selection basket, which one is the best one to pick for a particular use case, for a niche domain-specific use case that we have at hand, right? So to answer this question, we are here today. We'll talk about the challenges and get you the probable solution for the for this, and to optimize the process as much as possible. So hi, good morning everybody. I am Divyanshi Yadav, and I have with me Vipul Sharma. We are both data scientists at Genpact. Starting off, so today we'll walk you through the business challenge that is at hand, and we will also talk about the solution that we have to offer for you. The methodology, we'll go through it, the experiments, the metrics that we use, the results that we got, and we'll finally conclude it. At the end, we'll take all the questions that you have. So starting off, I just mentioned that we have many models at hand, right? Now this, on the right-hand side, is a snippet of DeepSeek R1's research paper, which clearly shows the scores that it has achieved in multiple benchmark data sets that there are in different use cases. And there's a comparison with the other models that there are. So we can clearly see that even the best model that is claimed to be the best model right now is not performing well in all the possible tasks, right? We can see that it outperforms OpenAI on maths, but OpenAI's O1 is performing better in 3 out of 5 benchmarks for coding. So of course, for coding, you would go for O1, but for any math problem, you would probably pick DeepSeek R1, right? So selecting the right model for yourself is a challenge, and given the use case, now you want to pick the right model. There can be multiple use cases. For example, you want to make a use case, you want to create a system that can update your code with every Git commit that you have. As soon as your software pipeline updates, you want to update the documentation. Or there can be a verdict decision-making software, anything. And you want to get the right model for it. You cannot choose a model randomly. You have to try it and test it and do hit and trial multiple times, which of course incurs a lot of cost and all. So for this problem, people came up with fine-tuning. The industry nowadays fine-tunes smaller models to make it a best fit for the domain use case that you have at hand. And we have seen it working pretty well. So a smaller model, here InstructGPT, which is just 1.3 billion parameter model, if fine-tuned on a particular data set, is seen to perform better than a larger model which is GPT-3, just a pre-trained model, with 175 billion parameters. So we have seen fine-tuning is working wonders, right? But now, which model is to be fine-tuned? On what data, with what parameters, is also a question, and we do trial and error for that as well, right? So how many of you are comfortable with model fine-tuning? How many of you have worked with it? And how many of you are aware of the challenges that we have in model fine-tuning? Yeah, I can see there are a few hands going up, but I'll just reiterate for the rest of you that while fine-tuning a model, there are multiple challenges that we face. There is data, of course. There is infrastructure. There is cost that is going to be incurred, et cetera, et cetera. But why we are fine-tuning the model? Fine-tuning is just that you're taking a pre-trained model, you're ingesting some domain-specific data to it, and you're making it used to your data. which helps the model to understand the use case, the data, and it performs in, increases the performance of your base model. That's it. So yeah, so you help the model to acquire some domain-specific knowledge, which enhances the performance of your base model. It is a cost-effective approach. Rather than using a larger model and assuming that a larger model will suit your use case, it's better to go for a smaller model, fine-tune it on your data set. You might get a better accuracy, and you might save up some money there. Then we've already talked about this one, and most of the open source models are open for fine-tuning, and some of the proprietary models are there, and you can fine-tune them. Going ahead with the challenges, so fine-tuning a model incurs significant amount of cost. You need separate infrastructure. It is to be provisioned for your fine-tuning. Then the data quality is directly proportional to the quality of your fine-tuning. The better the data you provide to the model, the better accuracy you would see at the end. Then the hyperparameter, even if you take care of the first three, right, the infrastructure, the cost, and the data quality, if you take care of the first three, the last two will still give you a hard time. So choosing the right hyperparameters and choosing the right models will take multiple iterations of trial and error, which will take a lot of cost, time, money, effort, etc. Now, how can we save up some money here? How can we save up some time here? So we are kind of sort of there with the business challenge and the use case, that there are multiple open source models and we want to search the right one for our use case. Multiple experiments are to be done to get to the right model. We want to save some money, and I'll just skip through it. And then coming to the objectives, that we want to design a data-driven solution that can help you get to the right model and also give you the right set of hyperparameters as a byproduct. We want to optimize the process, save time. Yeah. So now we are coming to the framework that we are using for this entire thing. So we start with a user that has a particular use case at hand, right? And some data set. The user has to give the framework some set of data and some use case description along with a minimum accuracy threshold that is expected. Minimum can be 80 and max always remains 100, right? And an evaluation script is to be given by the user. Now, the data set goes through a generative AI model. This data set is broken down into subsets, and each subset is representative of the whole population. So we stratify the data set, and now this stratified random sample of the data set and the rest of the metadata is again sent to a generative AI model, and we choose the right benchmark for that use case. Now we refer to the leaderboard for that use case, and we pick the top 10 models that are there according to the leaderboard. There are multiple leaderboards available. We pick the top 10 models, and we use the 4-bit quantized versions of them. We pick that, and we train it with different set of hyperparameters like alpha, LoRa, etc., etc. And post that, we use a custom model selection algorithm, which we will be talking about in the next coming slides. If we get to the right amount of accuracy, we come out of the loop. If we are not there yet, we have not found out the most optimized model with the least amount of cost and infra that is required, we reiterate and we check the other models that we have. Over to you for...
Check. It's working. So thank you, Divanshi, for giving the good overview of the solution design that we have in place, or the framework that we can say. So while the entire fine-tuning process, the many of you who would have fine-tuned before, they must know it. But you would have noticed a version that you might not have seen before. That is the customized model selection algorithm. Now, this is not something that is available out there in the market. This is something that we came up with, and I'm going to show you through how did it actually work. So please stay focused for now. So while we select 10 models for our fine-tuning processes, 10 models is a bit too much to show on a slide. So for example, I have picked 5 models. These are some sample models that I have on place. they are all arranged on their model size, or you can say that training billion parameters, how much the size the model has, they are sorted in an ascending order based on that. Now, it is always safe to start with the middle value. So what we do first is we pick the middle model that is available in the top 10 leaderboards model, and we fine tune it based on all the hyperparameters tuning that are in place, and we see whether the minimum accuracy threshold that Divanshi has already mentioned is being met or not. So now there are two cases will be arising. What happens when the accuracy is being met, and what happens when it is not being met? So I'll like you to come to the second diagram here. Is what will the custom model selection algorithm do if the accuracy is met? Now the whole aim of this experiment is to give you the least model size, or you can say the most optimized size, which you can use for your use case with the minimum cost, minimum infrastructure requirements, and all of the above things. So while if we meet the accuracy threshold with model 3, it is still possible that we might be able to meet the accuracy threshold with smaller models as well. So now the testing goes on to the left hand side, or the left hand list, which will be in a scale of 1 to 10. If the models are from 10, it will be like 1 to 5 along. So in those 1 to 5, now we have a smaller list. In those, again, we go for the middle element. Here it is just 2, so it goes for the middle element. It will check now whether this middle element is being able to meet the accuracy or not. This will go on till we are able to optimize it further. Now what happens if the accuracy at a certain point is not being met? So this is the third case. If the accuracy is not being met, then the model shifts to the right side. Now why this right side? You can understand this with your intuition. Is the whenever you use certain models, as the size of the model increases, the general observation is the capability of the models, and the accuracy of the output increases as well alongside. So if a certain model at suppose 15 billion parameters model is not able to perform well on your use case, what you do? Maybe you should go ahead for the model which is more capable in the list and that is available. So now the shift goes to the right hand side, and again the same process repeats, that the half of the list, the middle element is chosen, or the middle model is chosen, and that is hyperparameterized, fine tuning is done, and the accuracy is being met. Now at a certain point, it is possible, it will happen at a certain point where there is no going left or right, and you will be stuck with a model, or you will have the model with which will be giving you the target accuracy with the minimal set of hyperparameters. Now or the model size, that will be the most optimal model for your use case, and the solution will be able to give you the name of the model as well as the hyperparameters on which it was able to give you that result as well. This saves a lot of time, because earlier this whole set of hit and trial experiments were manual, and a lot of resources, money, time, infrastructure was invested in this. Now this entire thing is a data driven pipeline which can accommodate all the changes that are needed, which earlier required a human in the loop. Okay, let us go. So this is the example of how the model selection algorithm works. So the use case here is a summarization of email. We have picked a use case simple enough to understand for all, so everybody has a go at it. Now there are 10 models that are selected. All are open source and arranged in a ascending order of their model size. Now what happens? I'll like to see to the table here. At first step, the middle element is Llama 3.18b. That is fine-tuned, but the minimum accuracy threshold, as you are able to see in the above, it is 90% set by the user. The user wants nothing less than 90%. That is a breakup point for him. But the model gives 73%. Is it able to meet the target accuracy? No. So what happens? If this model is not able to meet, we go for the larger models. So now there are 5 models left which are on the right. Now in this 5 model, in the second step, we go for the middle element once again. You can check, and the accuracy is 86. It is still not able to met, but now we are left with 2 models. Now in the third step, we go ahead for another model. Now it is able to give you 92. And here, while the accuracy is being met, we stop, because now there are no more models left to optimize it. Now if this would have met here, then we would have got to the left hand side to see if we can fine tune or we can optimize the size of the model to reduce the cost or the overheads in the long run. And the conclusion for this experiment will be Llama 3.370b is the go-to model for you to choose, which earlier required all 10 set of model experiments. Now how many experiments did you do? You did 3. The complexity for all the SDs here in this room, the time complexity reduces from O(n) to O log n. This is the drastic improvement. Now this is 10, as in when the size of the models or the length of the list increases, the difference in the cost and the time invested will be huge. Okay, so going next. So let us talk about the optimizations here in place. There are several points where we have optimized the solution compared to the traditional approach. The first is the optimization of data set. So please refer to the solution design that we first shared. How the optimization of data set is taking place? It is taking place due to the stratified random sampling data set that we are using. It is a much smaller data set. Optimization of model pool. Now we are not testing on every model. We are only testing on the models that are tried and tested and are on the leaderboards. So optimization of model size, because we are fine tuning, the entire set of experiments are being done on the 4-bit quantized model size. So the optimization of model size is taking place as well. Optimization of hyperparameter tuning. The user does not need to do anything. The entire pipeline will be able to give them the best set of hyperparameters for that particular model. And the last is the optimization of model selection. Now the entire model selection is of the time complexity O log n instead of the On that we are used to before. Coming to the evaluation and experimentations, the data set I have already mentioned. It is a summarization of emails on which the entire set of experiments were being conducted. Few of the experimentation evaluation metrics or the key points are here is models with the improved performance. We are able to get the model which will be able to give the minimum accuracy threshold with the minimum size. So the model performance improvement is evident. There are insights on evaluation. What are the insights? Now there will be cases of hallucination as well, which all of you must be familiar with. So those cases will be highlighted on the evaluation script itself. The latency, the cost incurred in the fine tuning, everything will be laid out to the user as a cost or metric report, and they will be used to they can use it for their own decisions, and this will give them a great insight on the entire experiment. And higher productivity. The fine tuning experiments on these 10 models, which earlier would have taken 3 to 4 weeks to complete it in its entirety, now can be done in a matter of few days and with minimal resources as well. The results, I'll go through the two charts here. The first is the memory optimization, because the 4-bit quantized models is almost 1/4 of the size of the full model for fine tuning. So a person who is fine tuning a full size model will be incurring much more cost or time requirements on the GPU than the 4-bit quantized models, and the 4-bit quantized model is something that we use. So the optimization on the memory footprint is pretty evident. The most important result for this is, if we would have gone for the traditional method for this experiment, it incurred us around $232. However, with our approach, the entire thing, the similar results, similar set of hyperparameters and everything, we were able to get in 81.2. This is a drastic improvement in the cost efficiency. We are able to save almost 65% of the total cost that is being incurred without being compromising on anything. Now, improved efficiency. The entire process is being more efficient. I will not spend more time on this because we have already talked about the optimizations here. Cost saving opportunities, almost 65%. That is a phenomenal number for a fine tuning experiment, as well as the time that is being saved. So that is also extra. Reliable and optimized solution. While the entire solution is robust, it still provides the user the flexibility to change anything. They can change the number of models from 10 to 20. They can change maybe a different algorithm or something. So entire thing, it is, while being flexible, it is still robust enough to not compromise on the efficiency of the solution. And this takes us to the conclusion slide, where the entire solution is data driven, and data driven often brings in the more trust from the business side. The solution is highly optimized, as shown in the second point. All the optimization points we have already mentioned, and all the redundant parts of the fine tuning are being removed. The entire fine tuning experiment, the model selection part is being optimized. The cost saving is pretty evident. The time saving is an additional, and one more extra thing is the requirement of less human resource to get the same results that we were able to get with the earlier experiments. So thank you guys for being a good listener. That takes us to the end of end of this presentation, and we'll be open for questions if there are any.
Thank you, Vipul. Thank you, Devanshi. The floor is open for questions. If anyone has one, I think a lot of questions. Okay. So could we have the mic, please? Yeah.
Yeah.
And please introduce yourself and what you do before asking question, please. Yeah.
Yeah, sure. Yeah. I'm here. Yeah. I'm Tejasvi. I'm working as a data scientist at Synchrony. We are a bank. So a wonderful presentation. Thank you. One quick question is for the email summarization example, right? What was the benchmark leaderboard metric, right, that you were using? Because there are different leaderboards, different benchmarks. So just wanted to understand how did you pick the right benchmark metric as well?
Okay. So for the English proficiency exam, for the English proficiency test, there are few metrics I can show you. I'll go you both. I think the first slide which Divyanshi showed focused on that only. We'll take question. Okay. So this part is for the English part. Now of course, even for the English there are a lot
Right.
of benchmarks available. Now we went ahead with MMLU and the GPQA Diamond. There are few reasons. Like in all of the research papers for whatever the new model that are being released, you will first see the numbers that are being quoted for MMLU. That is one of the standard English benchmark datasets which shows the proficiency of a particular model on generalizing the efficiency on English task. Now summarization itself is a pretty English intensive task because sorry, just the disclaimer, the entire dataset was in English. Okay, so the MMLU, this gives a very good idea of how the model will perform in general in all the English tasks. Like I'm not talking about the reasoning, only the English intensive tasks. So yes, that is what we have used to shortlist the models.
Okay. Thank you.
Uh, Hi. Just wanted to understand on the hi. So just wanted to understand on the hyperparameter selection. So as you said that you were iterating on a lot of models, right? So
Mhm.
for example, every model will have its own set of hyperparameters. So for example, just to give you a very random example, LoRa depth, right? So for some of the smaller models, larger LoRa depth might work. For larger models, might not work. So how do you come up with the set of hyperparameters for each and individual models? So if you can elaborate a bit on that.
Yes. Okay. So the during the introduction itself, what we mentioned is the entire fine-tuning experiments were conducted on the QLoRA fine-tuning technique. Now the QLoRA fine-tuning, while it has a lot of parameters to fine-tune as well, uh, we used few of the metrics that made the most changes based on our experimentation. That is the rank and the LoRa alpha.
Okay.
So these parameters, based on our experimentation, changing them were drastically affecting the results that were in place. Now, of course, there are a lot of parameters. There will always be question on why not we optimize the other parameter. There's always a scope for increasing. Now, as we increase each hyperparameter, you already realize the complexity of the entire solution will go exponentially. So we picked only the worst because the entire use case behind this research paper is to optimize the entire process of model selection and coming to a conclusion that was not so quick in the traditional methods.
Okay. Thank you.
Yeah.
Sure.
Thank you guys first of all for this lovely session. I just have two questions. First was related to you are using 4-bit quantization. Did you do experiment with like 8-bit or something, or is just like across all the model that you are using is remain that?
Uh, so the reasoning here was backed by a few things. There were few experimentations done on various frameworks. One of them is Unsloth. I think you might have heard
Yeah.
of it. So they offer the while 1 billion on all are there in the market as well. But based on our experimentation, the 4-bit model, the 4-bit quantized model,
Okay.
they were pretty efficient or pretty close to the 16-bit model, which the accuracy drop while in the 1 billion parameter there was still significant that we would
Okay.
because we want to make an informed decision of how the full model fine tuning will work in the production.
Understood.
So we did not want to go so low that the 90% that the full model would have given, now the 1 bit is giving 72 and we might would have missed that. So that is why we went for 4-bit, so we can retain the most of the efficiency of the model while not compromising with the accuracy.
Okay. And second question was related to your initial infra setup.
Mhm.
So I could see in your chart here go from 8B to like 70B. So initial your setup is started. So you take the worst case like to handle the 70B model, right?
Mhm.
I mean, so your initial.
Your question is here, right?
Yeah, my question is here because you started with I think 8B and then you go up to
No,
70.
that is 3.8p.
Yeah, I read 3.8B, and
Yes.
then you like final one that works for you is 70B. So your initial infra setup was able to handle up to that case, because in each model selection that your infra will either
Definitely,
evolve
definitely.
or decreases.
Yes, yes, the infra question is definitely something that is most challenging. So what happens here is it is something very interesting. For if we are talking about a full size model,
Mm-hmm.
the GPU that we will use for fine tuning it will change drastically. Like a simple A100, I'm talking about just Azure. A simple A100 for the most of the till maybe half or sixth of the models would do just fine. After that, we'll have to raise the bar
Yeah.
of the A100s, and maybe the last one will require the maximum A100 or maybe the H100 that is in place. However, with the 4-bit model quantizations, that is something that we are able to solve for most of the models.
Okay.
Because the 4-bit model consideration, it directly almost one-fourths the model size. Now with just you can optimize the secondary storage of the compute, then you will be able to fine tune almost all of the models.
Okay, makes sense. Thanks again for answering.
Yeah.
There's one
Uh,
more question.
yeah, great presentation. Thank you so much. I had one question. It's in this slide only. So when we're dealing with models from different companies, let's assume we started with a model which is in between the list, and it does not meet the threshold.
Mhm.
But if there is another model which is of less parameters, but if on fine tuning could perform better, it's on the left side, but we are not choosing it, right?
Mhm.
What would be the case in that?
Okay. So there is one thing, like suppose I would like to take this with an example. Suppose the middle, as you have said, in the middle scenario, the middle model is chosen and it was not able to meet up accuracy. Now, by default, the algorithm will ask it to go forward. Okay. Now the go forward, it comes with two cases as well. There is a potential that, as you are saying, maybe a newer, smaller, more efficient model is launched and it might be there and it might be missed if we go forward. Now there is a catch. If going forward, if that solution itself does not give you the result, we will still revert back to the original method of we will pick all of those 4-bit quantized models that are left to see if we are able to still reach the efficiency at this point. Now why is this important? Because while optimization that is able we are able to do in 90-95% of the cases, but there might still be 5% where the algorithm definitely can miss. So that is the safeguard that is in place to ensure that these models are not missed.
Okay, but if the model which is performing better, if the right side model
Mm-hmm.
has met the threshold,
Mm-hmm.
but the model which is on the left side would be more efficient, right, in terms of GPU usage and other parameters if you're taking in consideration.
Yes. But this whole algorithm is based on the assumption that I have already highlighted. Is we often, like, this is not always. Of course, there will be change with time. We often come across these cases that the models, as they increase in the model size, the training billion parameters, they increase in their efficiency as well. So that is the whole. That is where the whole algorithm is based on.
So although your point is extremely right,
Mm.
right? But the likeliness of that happening is very low. So we assume that we'll.
Yes.
I have the follow-up question on that. So if you are saying that the assumption is that the heavier the model, the better the model, and if you have the infrastructure that can handle 70 billion, why not directly go with the 70 billion? Why even try maybe 8 billion or 5?
That is a very you want to take. Uh, that is a very good question, in fact, and that is where the entire use case of this research paper comes into the play. What we discussed earlier is we are aiming to provide the accuracy threshold that the user wants with the minimum cost and time. Now, how will ensure minimum cost? The deployment cost for the model increases exponentially as the model size or the model complexity increases. Now we can definitely, that raises the question that why did we go for the open source model in the first place? Why not directly go for the OpenAI O1? That is charging $15 per million token for input and $60 per million token for output. Now directly just deploying O1 in the solution might not be the best possible solution that you have. In client's projects or something, the client will always have some budget constraints, definitely will have some compute constraints or some other policy restriction that they cannot deploy the bigger models because of the cost, because of the latency. Suppose you are using a real-time application. These reasoning models, as you go through the bigger models, the time also increases. The smaller model, that is where they excel the best. So that is where the just directly going for the bigger models will backfire.
Got it. Thank you.
Thank you. Thank you, Vipul and Devyanshi. That was a brilliant presentation. Really amazing to see the fine-tuning cost reduced to less than 60%, you said? 70%? You said 60, right? Thank you so much.